Hi, and welcome to this section of the Probability and Statistics Tutor. And in this section, we're going to switch gears just a little bit and tackle the topic of mathematical expectation, okay? This section has a long name. It sounds really formal and complicated, but actually it's one of the shortest sections in the whole thing here and one of the easiest to understand. So mathematical expectation, what does it mean? Just like I usually do, I want to start out with an example because I think it'll make it easy, okay? Let's say there's a raffle at the school or something, and there's 1,000 raffle tickets, and you buy one of those tickets. And the grand prize is, what is the grand prize? $500, okay? So you know that you're going to buy one of these tickets, and there's a chance you're going to win $500, okay? There's also a very likely chance you won't win anything at all. Okay, that's the way it is with raffle tickets or lottery tickets. Okay, so what you know in specific is, if you think about it, you know that only one person is going to win this thing, and so then therefore 999 people are going to actually lose, and that's assuming all the tickets are sold, right? So one person wins and 999 people lose. So it's not very great odds you're going to win anyway. The winner is going to get $500. And 999 losers are all going to get nothing, $0. So it's a winner-take-all kind of thing. That's what a lottery is, okay? So if you engage in these things, right, as a human being, because you're hoping that you're going to be the one that wins. You're going to be hoping that you're going to be the one that actually wins the $500. But you know in your heart that you're probably going to be one of the 999 people that gets nothing at all, okay? But on average, what would be the expected value coming out of this thing? On average, okay? I mean, you know that you have a chance of winning $500. You know there's a very likely chance you'll win nothing, but if you look at everything on the whole, what would be the average if you did this experiment over and over and over and over again? What would be the average amount of money that you would win? Well, if we look at this, we could say that the expectation, the mathematical expectation, it's a big word, that's all it is, for this experiment would be equal to, and I'm just going to tell you what it is, the probability that you're going to win, which is 1 out of 1,000, one chance to win out of 1,000 tickets, times the grand prize, which is $500. Okay, now let's take a look at this. What's this going to be? 500 divided by 1,000 is going to be 1/2. The unit is dollars, so 50 cents. That is the expectation. What does this mean? Okay, 50 cents. This means precisely the following thing. It means that we know that there's a chance I'm going to win money, a lot of money, $500, but we know the odds are very low of that happening. So if we look on the whole, on the average, then if I did this experiment a whole bunch of times, millions of times, on average, I would win 50 cents. Sometimes I'd win the $500 every now and then. Most of the time I'm going to win nothing at all. But on average, if I ran this experiment and entered 5 million lotteries, on average, I would win 50 cents, if you look kind of at the whole, if you average it all out, okay? And that's all it is. So this leads you to the definition of mathematical expectation that you'll just see in your book, and basically it goes like this. It says, if the probabilities of obtaining the amounts A1, I'll explain this in a minute, A2, A3, ... up to AK are equal to P1, P2, P3, ... PK, then the mathematical expectation is denoted by the big letter E, A1 times P1 plus A2 times P2 plus A3 times P3 ... all the way up to AK times PK. Now you see, this is why I always like to start with an example, because when you're given a formula like this, you're probably going to look at it and fall asleep and say, what is this talking about? What does this mean? It's nothing more than what we've talked about here, but this was a very simple example with only $1 amount and one probability. But if you know the probability of obtaining certain amounts of money are equal to these different probabilities, then the mathematical expectation is just the product of the amount of money times the probability plus the amount, whatever other amount of money times whatever other probability, plus so on and so on. That's all it is, okay? So let's go ahead and just use it. I think talking about it further isn't really going to help us any, but let's just go ahead and use it a few more times and you'll see that it's not a big deal, okay? Next problem says, what is the expectation if we win $10 if you toss a coin and get heads, and you lose $10 if you toss tails? So 50-50 chance of the coin landing on either side. If I get heads, I get $10. If I get tails, I lose $10. So someone could place a bet with me, and I know that in this single flip of this single coin, I have a chance to win $10 and also have a chance to lose $10. What I want to know is, if I perform this experiment 1,000,000 times, what is my winning going to be on average? Okay, so let's see if we can figure it out. Why don't you think about that as we go along here, and I think you can probably arrive at the answer without too much trouble in your head, but let's prove it. The expectation is equal to A1 times P1, this is the amount of money I win, times the probability that I've won that, plus whatever other dollar amount I win, times the probability of that happening. So, I said I win $10 if I land on heads. So this is $10. The probability of landing on heads is 1/2. Plus, the other dollar amount, the problem says I lose $10, so it's negative $10. And the probability of losing $10 is also 1/2, because if I land on tails, I lose the $10. So you can see right away, this is positive 5, and this is negative 5 when you do this multiplication. So what you're going to have, the expectation is $0 on average. So that's why I was saying I think you could probably arrive at that in your head without doing much math, because what's going on here, as you can see, is I know that if I'm in the school playground and I bet somebody $10 that I get heads and I'm going to win, I'm going to lose $10 if I get tails, I'm taking a chance on that one particular flip. The expectation, the mathematical expectation, is looking in the long run. It's saying if I do this experiment a whole lot, what is it going to do in the long run? Okay, I know that if I flip this coin 100 times, the chances are, or let's say 1,000 times or 1,000,000 times, the law of probability says, because the probability is exactly 1/2 of that thing getting heads or tails, roughly 1/2 of the flips will be heads and 1/2 will be tails if I do the experiment long enough. So if I lose half the time and I win half the time, the same amount of money, on average, I'm not going to win anything. So it's not very much to your advantage to keep betting over and over again, especially if you've won, because you're probably just going to end up losing, unless you have some way of influencing the coin, right? Okay, so the next problem says, a union negotiator feels that the probability of getting a raise is as follows. He's negotiating for his union. He feels that the probability of getting raises for his people are as follows in the table that I'm about to put on the board. What is the expected raise? Okay, so the table that I'm talking about here in this problem is the following. He thinks he can get a $1.50 raise with a probability of 0.40. That means 40% chance that I'm going to get this raise. Okay. He thinks that I have a 30% chance of getting a $1 raise for the union people. He thinks, or she thinks, that I have a 20% chance of getting a 50-cent raise. And of course, there's always the chance that you don't get any raise at all, because maybe you go in there and negotiate and they say, no, sorry, I'm not giving you any raise. There's actually a 10% chance that I won't get anything at all. So this union negotiator comes in, he thinks, look, I have a certain probability of getting these different raises. What is my expectation? What is my long-term, big picture, average outlook on this situation? What do I really think I'm going to get on average, given that this stuff is true? So the expectation is going to be $1.50 times the probability, 0.40, plus the next dollar amount times the probability that that one can occur, okay, plus the next dollar amount, which is this one here, 0.50, times his probability, plus the next dollar amount, which is 0, times 0.10. Okay, so if you actually do this, what you'll get, this times this is going to give you 0.6, the next one's going to give you 0.3, the next one's going to give you a 0.1, and the next one's going to give you 0. And so when you add all these up, on average, you think that you might actually get $1 raise. And this means on average. This means that he can go into the table and actually there's a pretty good chance he's going to get $1.50. Okay? There's also a very small chance he'll get nothing, and there's all the chances in between that he'll get these different amounts. But what this is saying, the expectation is saying that on average, if you had 100 negotiations with these same probabilities, on average, sometimes you would get higher, sometimes you would get nothing, sometimes you would get somewhere in between, but on average, you'll probably get $1 raise out of the deal. Okay, now the next problem says at the casino, if you play craps, you bet $5. Okay, there's a 244 divided by 495, 244 out of 495 probability that you'll win $5. And there's a 251 out of 495 probability that you'll lose $5. I'm betting $5, okay? So there's a probability I'm going to win, there's a probability I'm going to lose. What's my expected value? And what that means in the long run is, what's your expected value? That basically means if I do this experiment a whole bunch of times, what am I going to win on average? Okay, so let's figure that out. The expected value is in general, is just going to be the amount I can win times the probability plus the amount I can win times the probability, okay? Okay, and these could be different amounts and different probabilities. So what I'm going to have, I can win $5, but the probability of doing that is 244 out of 495, and that's just the probability that's given to me in the problem, and also maybe the casino publishes, that's the probability. Okay, or I could actually lose $5 because there's always a chance you lose when you play craps, right? And the odds of that is 251 out of 495. So let's see what we have here. The expectation is going to be equal to 5 times this fraction, when you convert it to a decimal, is going to be 0.4929 plus negative 5, and this one is going to be 0.5071. Okay? So what am I going to have here? I'm going to have 2.4645, this guy right here, minus, because of the negative sign, 2.5355. Okay? And when I do the subtraction, the expectation is actually going to be negative 0.071. Okay? And don't forget, this is actually in dollars. Okay? So this is the same thing as saying negative 7.1 cents. The expected value that I'm going to win is negative 7.1 cents. Now, what does that mean? That means that if I go into a casino, which is in the business of making money, by the way, taking your money on average, okay? Sometimes I'm going to win at craps, sometimes I'm going to lose at craps. But all the games are basically, rigged is the wrong term, but the probability is set up so that you're always going to lose in the long run. I mean, that's what casinos do, okay? Sometimes you might win big, but on average you're going to lose. That's what it means. And that's what this reflects here, basically. It says that if you go in, $5 I could win, $5 I could lose. But notice the probabilities were different. The probability of winning was actually less than the probability of losing. So in the long run, if I play craps all day, every day, even if I win really big sometimes, if I play the game long enough, I'm going to lose on average. Okay, and that's the average amount that I'm going to lose if I look at a long string of these things. So that was a short section on what I hope now is an easy topic for you, mathematical expectation. Okay, what it says is that when you're playing games of chance involving money, and by the way, that's the history of probability theory anyway. It comes from playing poker and other things. People tried to develop that math to help them win games, basically. And so what's happening in this section is you know there's a chance you're going to win, you know there's a chance you're going to lose. You know how much you could possibly win dollar-wise, and you know how much you could possibly lose dollar-wise. And so what you're looking at is you're trying to figure out in the long run, if I do the experiment long enough, if I play the game long enough, am I going to win in the long run, or am I going to lose in the long run? And if so, how much? So that's really the topic of mathematical expectation. It's not too hard. The math is certainly not too hard. It's just knowing what to do, just like anything else, and knowing what the results tell you. That's actually very important as well. And that's the topic of mathematical expectation.